right, welcome back again. So now we're going to be looking at the decimal side of things. But before we do that, there's a quick example I want to demonstrate about the density property of the rational numbers. So the property basically says that if we have two rational numbers, then we can always find a rational number between them. So no matter how close together you think two rational numbers are, two fractions are, you should always be able to find a number between them, another rational number between them. So it's pretty powerful rule. It just shows you how dense they are. It just keeps getting, you can keep getting smaller and smaller and closer together, but you'll always find another rational number between them. So to illustrate that, I want you to find the number halfway between 2/3 and 5/6. Now, it's kind of hard to wrap your brain around what process we need to follow, so let's try an example a little bit easier. What if we wanted to try to find the number halfway between 1 and 7? Well, let's take a look at the number line. The number lines is always a nice visual for this stuff. So if we said, okay, well, 1, 2, 3, 4, 5, 6, 7. Now, some of you might say, okay, well, 3.5. 3.5 is halfway between there. That's a good guess, but it's not quite right. But let's take a look at our number line. So we're looking at 1 and 7, and we want to kind of work our way in until we get to a point right smack dab in the middle. Now, in this case, you can kind of see that if we go 3 units in here and 3 units in here, that 4 is actually the number that's right smack dab in the middle. But now, how do we get 4 mathematically from 1 and 7? So how could we manipulate 1 and 7 to get 4? Halfway between 1 and 7. Well, the trick for this is going to be to add first. If we add 1 and 7 first, we get 8. But half of 8 is 4. So that's the two steps that we're going to have to follow. We need to add first, and then we can divide it by 2. So that's what we're going to want to do with 2/3 and 5/6. So let's do it in 2 steps. So the first step is we got to add. So we want 2/3 plus 5/6. Now, remember, if we're adding, we got to have a common denominator. So in this case, 6 will work. So if we change the denominator of the first one to a 6, what's the new numerator going to be? You got it. It's going to be 4. So we got 4/6 and 5/6, which adds to 9/6. Now 9/6, can we reduce that? Yeah, 3 goes into both of those. We can divide a 3 out. So that gives us 3 halves. So there's step 1. We've properly added them, and we got an improper fraction, which is fine. I would say leave it improper for now, because we still got a little bit more to do. We're not done with the whole thing yet. So step 2 is to divide by 2. Now, if we want to divide by 2, that means we're going to take 3 halves and divide by a snapped lead by 2. All right, so that's technically what we're doing. But now how do we proceed? How do we make this into a process or into a problem that we can tackle? Now, this 2, remember what we said, it's a rational number. Any integer or whole number or natural number can be written as a fraction. All we have to do is put it over 1. So if we do that, now we're good to go, because now we can change this using our switch and flip. So we got 3 halves, so the first fraction stays the same. Multiply it by 1/2. And now we can multiply across to get 3/4. So 3/4 should be your answer. And so that is the one application I wanted you to see. Now, the last part of this is looking at the decimal side of things. So now we know we can write a fraction as a decimal. All you got to do is divide. So 4 goes into 1.25, 10 goes into 7.7, and so on. So you have all of those divisions that you can just do it on your calculator. You know, if you're not sure, anytime you want to do a division, you always put the top number in first, divided by the bottom number, and you can see there's the decimal value of it. So always put the top number in first, and the second number is the bottom number, and you'll be fine. Okay? So that's a quick way to change it into a decimal. So in these cases, though, we can see they're all similar in that there's a finite number of decimal places. It doesn't go on forever and ever. So these are called terminating decimals because they stop eventually. Now, what about something like 4/11ths? Well, if we go to our calculator, 4 divided by 11, well, it looks like it terminates, but your calculator is not perfect. It rounds. Because there's only a certain number of places on your calculator, it's got to stop somewhere, so it rounds it automatically. But if we did it by hand, it does keep going and going and going and going. So this is equal to 0.363636, and it keeps repeating that same pattern forever. So we can illustrate that by putting 3 dots like this, or a shorter way is to use an overbar. And an overbar goes over the digits that repeat. So in this case, this would be 0.36 repeating. So that's the notation we could use as well. So if it's not asking you to round it, then you should kind of write the pattern either this way or this way. Now, can we write terminating decimals as repeating decimals? This is just, a fun fact. The answer is yes. We can write terminating ones as repeating ones. We know 3/4 is 0.75, but if we wanted to make it repeating, can we add a 0 to the end of it? Does it change it? No. Could we add even more zeros? Sure. We could add an infinite number of zeros. We could put an overbar over the 0, and that would make it repeating. Do we do that? No. That's crazy to do that. But we could. So any rational number can be expressed as either a terminating or repeating decimal. So that's the key ingredient to determine whether or not it's a rational number. Can it be written as a decimal that's repeating or terminating? So moving the one direction is pretty easy because we can use our calculator. But what about going the other direction? That's where it gets a little bit trickier. Now there's 2 styles of problems we're going to see. We got terminating ones, and how do we change those? But then we got repeating ones, which is a little bit more complicated. So let's start with the easier case. We got 0.437, so it's terminating. So how do we change that into a fraction? Well, the first step is to take that 437. That's going to end up being the top of our fraction. On the bottom, we're going to be putting it over 1 with a certain number of zeros. Now, what's that certain number of zeros going to be? It's based on where the decimal point is in the problem. So you can see we got 1, 2, 3 decimal places here. So if there's 3 decimal places in your problem, you're going to need 3 zeros on the bottom with a 1. So 437 over 1,000. Now, remember, if you're not sure, double check. If we divide 437 by 1,000, we get back what we started with. So we're good. Now, the only steps left to do is make sure that this is in lowest terms. So is 437 over 1,000 in lowest terms? You betcha, it is. So that's done. Let's try the next one. 0.85. So what's that going to look like as a fraction? 85 over 100. You got it. So 85 over 100. But now, are we done? We got to get this reduced down. So 5, hopefully, is sticking out at you. That's something we can reduce that down by. So 85 divided by 5 is going to be 17. 100 divided by 5 is 20. And so that would be in lowest terms. All right. So terminating decimals are always going to be a lot easier because it's putting it over 10, 100, 1,000, whatever. It all is based on what the number of decimal places is, though. When we're dealing with repeating, now it's a little bit more interesting. There's a few layers to it, and it has a little bit of an algebra feel to it. So hopefully it won't freak you out. I'm pretty confident it won't, though. All right, so now the first thing we notice is that we got 0.5 repeating. So that 5 is just going to keep going on forever and ever and ever. Now, I'm going to set it equal to a letter. I'm going to set it equal to x. And I'm going to write out some of that pattern. So x is equal to that. Now, I'm going to multiply it by a number. And that number is going to be some power of 10. So 10, 100, 1,000, something. In this case, though, I'm going to multiply it by 10. And I'll explain why in a minute. So if we multiply it by 10, if I multiply x times 10, that's just going to change to 10x. 10 times x. That's not anything too drastic. You're just basically slamming a 10 in front of it. But what happens to my original decimal if I multiply this by 10? What happens to the decimal point? It should move it over one spot. So I do want to keep my decimal points lined up because I'm going to be doing some subtraction next. So I'm going to say this is equal to 5.5555. And again, it keeps going on forever and ever. So you set the number equal to x. You multiply it by a power of 10, which we're going to determine a rule for it in a minute. Next step is going to be to subtract the 2. Now, all of these decimal places all line up. So everything is going to cancel up to the 5. So the only thing left after we subtract on the right side of the equals is a 5. But what about on the left? Now, the x's aren't going to just cancel out because you have to think of it a little bit differently. I like to use fruit as an example. If I had 10 apples and I take away one of the same type of apple, how many apples do I have left? I don't have 10 and nothing else. I have 9 apples left. So the way to think of it is to put a 1 in front of this x. If I have 10 apples and I take away 1 apple, I have 9 apples left. Now, it's a lot more compact, but we're not quite done yet. We still want to get a fraction out of this. So now here's the trick with algebra. If we want to get rid of this 9 and it's being multiplied by x, we need to divide to get rid of it. So the last step is going to be to divide both sides by 9, because on the left, those 9s are going to cancel out. So this tells me that x is equal to 5/9. Now, if you don't believe me, let's go back to the calculator. So 5 divided by 9 equals, and there it is. Now remember, your calculator is going to round. So it rounds that last digit no matter what. It either rounds it up or it doesn't. In this case, it rounds it up. So, but it will be your original problem. So let's try 2 more. And this video is going to be a little bit long, but not too bad. So what happens when we got 2 numbers repeating? Well, we still started off the same way. So we got to set x equal to the number and write out a little bit of the pattern. So 6, 3, 6, 3, and I'll do it one more. So there's our number. Now, if we multiplied it by 10, well, let's see what happens. Remember, if we multiply it by 10, that moves it over one spot. So that means we're going to have 6.363636. Nothing lines up. But if we multiply it by a little bit higher power of 10, let's say maybe 100, then it's going to move it 2 spots. So if we multiply it by 100, that's going to get me to 63.636363 and so on. Now everything lines up. So you're always trying to make sure those decimal places line up so that way they all cancel when you subtract. So the trick is, look at the bar. The bar is over 2 numbers, so you multiply it by 100. If the bar is over 1 number, you multiply it by 10. If it was over 3 numbers, you multiply it by, you got it, 1,000. 1,000 would be what you'd have to multiply it if it was over 3 numbers. So that's the trick, that's the pattern. So once you've done that though, now you can subtract again. So all of these decimal places cancel right up to the 63. And then what are we going to have on the left side? 100x minus x. And remember, this is still a 1x. So yeah, 99. 99x. All right. And so now, next step is to divide. So let's divide by the 99 on both sides. So those cancel. So we got x equals 63 over 99. So are we done? Is it in lowest terms? Well, we do have a common number that we can divide out. 9 goes into both of those. So 63 divided by 9 is 7. 99 divided by 9 is 11. So 7 11ths. And again, if you're not sure if you did it right, just use your calculator to do a quick check. So 7 divided by 11, and there it is. So, okay. So we got one more, and then that wraps up this section. So we're back to one decimal place being covered by the overbar. So we know what we should have to multiply by. Let's see. Now remember, just the 3 is repeating, not the 7. So it's a 7 with a bunch of 3's. Now because it's over one number, we got to multiply it by 10. So 10x, and then the decimal point moves over one spot to the right. It's pretty critical that you keep all those decimal points lined up, because otherwise it's going to throw you off as well. So we multiplied by 10. Now we can subtract. So we got some 3's that are canceling. And it cancels right up to there. All right. So we're going to have some decimals when we subtract this. So 7.3 minus 0.7 is 6.6. Well, we got to deal with it. We're going to deal with it. What about on the left? Same as up above, we're going to have a 9x. Next step is to divide. So x equals 6.6 over 9. Well, we got a couple of problems. First big one is that we got a decimal in there. And remember, the instructions said a quotient of integers. So decimals are not integers, so we got to do some work to fix this. Now, very similar to what we did up here, if we wanted to move the decimal point over one spot, all we have to do is multiply it by 10. But if we multiply the top by 10, we got to do the same thing to the bottom. So that's going to change this to 66 over 90. So now we have integers. So the last step we got to do is try to reduce it. So what goes into 66 and 90? Well, they're both even, so we know 2 does, but is there something bigger? And I think there is. I think 6 goes into both of those. So 6 goes into 66 11 times. 6 goes into 90 15 times. So that should be your answer, 11/15. And again, it doesn't hurt to double check. So 11 divided by 15 equals 0.73333, which is what we got. So we're good to go. Alrighty, so hopefully that helps you get through this section. Next section is going to be getting into 6.4, which is all about irrational numbers. Woohoo! We'll see you in the next video.